Okay, so Chapter 10 discusses interrupts. Interrupts are what make microcontrollers so powerful because we can have low priority tasks and high priority tasks. So here's our agenda today. Okay, a lot of stuff going on in here, and hopefully by the end of class we'll be able to start talking about the lab today. Okay. So the way we've had to do things, like when you were looking at a button, we've had to do some type of polling. Go in a loop forever, and you say, all right, if a particular pin is low or if a particular pin is high, what that does, though, is it means you can't do anything else. To poll a button while doing a 7-segment display is quite difficult because time division multiplexing requires that you sit there in a busy wait loop from 4 milliseconds. So that's not going to work. Interrupts, they greatly reduce the load on the CPU, all right, because they offload that processing, that polling, to additional hardware. We can have lots of things that cause interrupts, okay, and we can also turn off some interrupts. So this is my favorite joke of the whole semester. Somebody raise your hand to be my guinea pig. Knock, knock.
Who's that?
Interrupting cow. Moo! Interrupting cow. Yeah, anyway, so that's what interrupts do. They stop the processor in the middle of their very normal and lackadaisical task, and they do something else, and then they go back at the end. Okay, so now you just sit here and you're doing whatever the heck you feel like. Delay, do some stuff, blah, blah, blah. But as soon as pin D2 goes low, magically, we'll explain the magic in a second, right? Something's going to happen. We're going to stop doing our common low priority task and handle that interrupt. So how many things can cause interrupts on the 328P? Well, there's a lot, right? There's a ton. Each of these has a special name, and what I don't seem to have is my clicker. That's quite upsetting. Each of these has some special function. You'll find things like external pin interrupts, that's one of them. Things about timers, which we have talked about, right? Timers have overflows and compares. So instead of sitting there and polling for a flag, we can actually just say, hey, tell us when this happens. And tons of other peripherals we haven't even talked about yet. Okay, they exist. Get out of the way. There we go. Show this slide again. Okay, so the interrupt unit is actually a separate peripheral, okay? And the main thing that it needs to talk to the CPU about is whether or not we've enabled interrupts. There is a flag inside the status register, so in addition to N, Z, and C, and half carry, and overflow, and so forth, there's a bit called the I bit. Normally that bit is 0 on boot up. When we turn it to 1, that enables the interrupt unit, and it can start doing things. Okay. There are also tons of registers associated with this. So there is one for pin change interrupts, int 0, int 1. There's one register called TI mask 0. That deals with the interrupts for channel 0, timer channel 0. And there's an interrupt pin for each. Compare B, compare A, and the overflow. And they all follow the same format. OCIE. IE stands for interrupt enable. Output compare, interrupt enable. TOIE, timer overflow, interrupt enable. They're designed so that you can read across and it's easy to say. Okay? Now, along with every mask register, because we can turn these on and off one at a time if we want, there's also a flag register. Now, these flags, we've already talked about these flags. We talked about the timer flags last class. We said that when an overflow occurs, that flag gets set. So this is the TI flag register. And when an event like an overflow occurs, that flag gets set high. Now, when that flag gets set high, for example, TOV gets set high, if the interrupt enable bit is set, not only will that flag get set high, but program flow will change. Okay? We will stop doing our common main task, and we will instead go to an interrupt service handler. Okay. Just check a few things here. Okay. So the first interrupt source that we're going to talk about are external interrupts. Here's the 328P. There are two hardware dedicated sources of interrupt. They're not the only type of interrupt, but these are the lowest level. They can wake out of deep, deep sleep mode. int0 and int1. They correspond to pins D2 and D3. So if you hook up a button to those, it's actually very easy to get interrupts working. Now, where is the button on the analog discovery board? Not the analog discovery, the explained mini board. What's that hooked up to? I don't think it's D7. B7, yeah. So obviously this approach is not going to work for the button on the board, but it is important to know. I got to get rid of all this stuff. Okay. So let's talk about what happens when we're executing an interrupt. It's in assembly again. We'll be okay though. The important thing to note here is that I have this function down at the bottom, and it's effectively, what is it doing? It's exclusive ORing port C, outputting port C. It looks like it's flipping the 4th bit. Okay? Right? Takes in port C, exclusive ORs it with an 8, that's a single bit, and then outs it again. So that's all that happens. When you press the button, C0, 1, 2, 3, C3 is toggled. So I've got this looks like a function, right? Return, and then I've got a main program, and eventually it goes here, jump here. Okay, so it's staying. Now, where things get interesting is up top. You're used to this, org0, jump main. We've been doing that for a long time, and I haven't really said why we do that. I just said take it on faith. Well, it's because address 0 in program ROM is a vector or a pointer to a particular interrupt, the reset interrupt. So on reset, it goes to address 0 and it does whatever it says. So it jumps to main. Address 2 is the location for another interrupt. This is our newest interrupt. It's called int0. Int0 just says something has changed on the int0 pin. So this is the ATmega32, and there's the int0 pin. It's also pin D2. So as we run this, okay. Whoa. No, go back. That was too fast. As we run this, it's going through and it's running this whole thing. One of the things that it's important to do is set up the stack pointer because we are using functions. Now, at some point right here, by the way, this intermediate code is actually setting up the interrupt, enabling it. We'll go over how we do all those things. The last step in enabling interrupts is to turn on the status register bit saying enable interrupts. At that point, interrupts can fire at any time. Okay, so let's say that we're right here. We're in the middle of executing some code. Okay, and at the time that we're executing that code, suddenly we change pin D2. Okay, pin D2 is changed. What it's going to do is almost like an implied function call. It's going to put the address of the next instruction that we would have executed onto the stack, just as if we'd done a call. Then it does an intermediate step, and the animation is ahead of it here. Did an intermediate step, it went to the interrupt vector, the interrupt address, 02, where it found a jump to the exclusive OR routine. Okay, so here's the exclusive OR routine. It's called an interrupt service routine. All things that handle interrupts are interrupt service routines. And it executes, so it twiddles the bit. Now, I said that this was just like a function and had a return, except this isn't the return instruction. What is this? This is return I, return from an interrupt. So it's a very subtle difference, okay? But it's going to do effectively what return does. Return takes this off of the stack, throws it back into the program counter. Let's watch. Boom, return, throws OF back in the program counter, stack pointer increases, and we're back where we were. Now, as far as this code is concerned, nothing has changed. It was executing this instruction, and now it's executing this instruction. There is nothing in this code to indicate that a call occurred there. So super awesome. However, it comes with a whole host of problems, okay? There are a lot of things that if you don't pay attention to them can go wrong. So the pros of interrupts, it simplifies your code. You don't have to worry about, okay, I'm going to output this segment, then check the button, then output this segment, then check the button, and do some kind of interleaving. You just say, all right, set it up. When the button is pressed, handle it with this routine, and then go back. Okay, so let's talk about the interrupt that we just set up, all that gobbledygook in the middle. Just like most peripherals, there are configuration registers. So the main thing about hardware interrupts, things labeled INT0, INT1, is that they can be edge or level triggered. Edge just means a rising or a falling edge. Level means any time it's at a 0. Okay, it actually can't do high level interrupts, only low level interrupts. So to do that, since we have 2 pins, we've got int0 and int1, there are 2 configuration bits for each. Okay, they're called ISC, interrupt sense control bits. And basically, depending on the combination, either it's a low, any edge, falling edge, or rising edge. Since at this point I think you guys have learned that it's good to get last year's exam, I will tell you that there's always some kind of a question on the exam saying set up a interrupt using rising edge or falling edge or low. I mean, I changed it up. So first thing you have to do is configure the peripheral. So this is the external interrupt peripheral. And we say we want either bit 0 or bit 1, int 0 or int 1, to have some kind of an interrupt associated with it. Otherwise, it's just a regular pin. It's just pins D3 and D4. Okay? So, a way to do this, and this goes back to my pet peeve, right? My favorite damn pet peeve. Right out of the book, load 2 into this register. Better way might be to say, put a 1 shifted by ISC01, a 0 shifted left by ISC0. Shifting a 0 over any number of places still gives you a 0. Okay? But it lets you know that you're setting it up. This is my preferred way. Okay, this is how I've settled on my way of doing things. I will say 0B10, which is the binary equivalent of 2. And I will shift it to the left by the least significant bit in my 2 bits. So this is a 2-bit quantity, ISC01 and ISC00. So I shift it left by that. So that puts those 2 bits in the correct position. It's the way I like doing things. It doesn't have to be the way you like doing things, but it might help. Okay. So we configure the interrupt inside the peripheral. Let's go to timer interrupts, okay? Because timer interrupts are going to be part of Lab 4, okay? We have to generate, as a reference, a 4 millisecond-ish delay. So let's look at this. This is going to use timer 0 to generate a square wave on a particular bit, a particular pin. At the same time, we're going to be doing something mundane, transferring stuff from port C to port D. So this is really written for the ATmega32, but with very little changes. This could work for the 328p. All right, let's look at the beginning here. We first off have 2 org statements. 0 is our reset vector. 16 happens to be the overflow vector. At least that's what the comment says. Okay. Normally, when we're in C, we don't even care. But when we're doing an assembly, we have to look it up. Now, that being said, we actually have mnemonics. If you go into the 328p def.inc file, you can find the name of that vector and just put it in there. So it's a little bit more readable. And then down here, way past our interrupt vector table, at 100, we put our code. And what do? Well, we set up our stack. We set up our pin IO. Okay, that's pretty mundane stuff. Here's where stuff gets interesting. In red, I set up my peripheral interrupt, because each peripheral has some interrupts that need to be set up. So this says TOIE. Somebody tell me what TOIE stands for. What word does each letter mean? T is the easy one. Timer. O, overflow. I, E, enable. So, again, nice and easy to read code. Awesome, great. We know exactly what interrupt we're enabling. So then we output it to the TI mask register. Also in red, I do the second step. I globally enable interrupts. So it's a two-step process. First, you have to say which interrupts inside of a peripheral trigger interrupts. Okay, because a particular peripheral can have several interrupts. Then you globally enable interrupts. You do that as the last thing usually. So then what do we have here? Well, then we actually configure this. So we enable everything, but the timer actually hasn't been configured yet. So what do? We load up 32 or minus 32, set up normal mode. This right here is the equivalent of saying clock source equals the unprescaled clock. I missed that one. Okay, and then we go into a forever loop here. Okay, and the forever loop just in from pin C out to port T. Nowhere in this code you will not find a call to this routine, this T overflow ISR. It'll never happen. Okay, so we initialize the interrupts, we initialize the timer. Oops, go back. Now this actually doesn't solve the stated problem. Okay, this says generate a square wave. Okay, now inside the ISR, we do in fact toggle bit B5. Okay, however, it's only going to happen once, which is not what we want. Right? It's only going to happen once because minus 32 might be 4 microseconds for whatever this crystal frequency is and so forth. But once it gets to FF, we don't actually reset T count. And remember, I think it was you who said, isn't this going to have to be reset every time? And it does. This is not going to work. A better solution for repeating events is CTC mode. Because CTC mode, you just set one value, and now you can see that it's going to happen at fixed intervals. And that's how we generate a square wave. This concept is going to come back over and over again in Lab 4 or Lab 5, probably Lab 6. Maybe not. So let's look at this in C, or no, sorry, in assembly. So same stuff occurs, but now when we initialize the timer, we initialize it in CTC mode. Okay, we use a positive value. 9 is the equivalent of waveform generation mode CTC plus an unprescaled clock. We activate here in our red, this is our interrupt setup. We no longer turn on the T overflow flag, we turn on the output compare interrupt enable flag. Throw that into the TI mask register, timer interrupt mask. Okay, and then what do? We sit here and we do nothing. Right? We're just sitting in this loop. Now, forever, effectively, the timer will be counting. It goes off and it counts. Every time it hits this output compare register value, which we set to 39, okay, which means every 40 cycles, basically, it's going to trigger the interrupt. It's going to call this routine. So this loop can be anywhere in this loop. Could be on this instruction, that instruction, or the jump instruction. Doesn't matter. Whatever is happening, it will stop doing that instruction. Or rather, I should say, it's not going to stop in the middle of instruction. It stops before it goes to the next instruction. That's a better way of saying it. Okay. So if it gets an interrupt here, it'll finish doing the in. It'll jump, well, actually, it'll jump in 2 steps. It'll jump from here up to the vector, okay, the interrupt vector, and that'll tell it to jump to the ISR, the interrupt service routine. And what does it do? It toggles the bit, and then it calls return I, which will then send it back to the next instruction, out. Okay, so now we've seen that we actually have multiple interrupt sources. We can have a timer interrupt, we can have a button interrupt. What happens if I press a button at the same time as I reset here? Well, there's a couple of options, right? What's one option that could happen? If 2 people ask you to do something at the same time, what are your options? It's always funny. Engineers will always say ignore one of them. That's their first thought. Just ignore one. But that's definitely an option, right? We could ignore one of the interrupts. That's bad, though, right? If this timer is doing the spark plug in your car and it has to spark, right, do you really want to ignore that? That's not a good thing. What's another option? Well, you can't do both at the same time. What? Do none. Well, that is an option. We could basically say, screw it, we're going to lunch. Okay. What's another option? One after another is an option. And that's sort of where the AVR is. It'll push one of them off. How does it decide which one, though? Priority. We have to give ourselves a priority. So if I give you homework and Dr. Castlelingham gives you homework, obviously you do my homework first, right?
Yeah.
Well, at least you're honest. Okay. So there is a priority. And basically, the closer you are to address 0, the higher your priority. So reset has the highest priority. Then external interrupts. Timer stuff happens sort of in the middle. And then there's some more stuff down here. I'm not going to go into each one of these. It's a big list, but I'm sort of saying in general terms, there is a priority, okay, of what happens. So in the question that I just asked, if you press a button at the same time as the timer interrupt happens, which one gets serviced? The button, because the button has a higher priority. Now, once the button ISR is finished, it'll actually then go to the timer ISR after it, okay? So one of the things that can happen here, suppose that this isn't connected to a button, but to some kind of encoder wheel or something that's spinning a lot. If it's spinning very fast, you might not ever get to your timer interrupt because this will keep firing over and over and over again. Okay, so there is such a thing as a starvation. Now, what happens if we are, well, let's go back to our old analogy. Let's say I ask you to do something. Let's not use me because you guys hate me. Let's say a friend asks you to do something, and while you're doing that something, another friend comes and asks you to do something. And let's not say it's a friend. Let's say it's the dean. What do you do? Dean first. Sure, that makes sense, right? Because the dean is more important than the task you're doing. That's not how the AVR works. The AVR says, okay, I'm going to do this thing until completion. And this is why we need a return I. This is the magic that happens with return I. When you go inside an interrupt service routine, it automatically ignores all other interrupts until it's done with that. So when you start the program, you must use SEI. SEI enables global interrupts. When you go into an interrupt service routine, the first thing that happens is it disables interrupts. The hardware does it. So you can't have a friend come up and ask you for something while you're in the middle of helping another friend. Now, that doesn't mean that it's not impossible. You can manually turn the I bit back on in the status register, but you better have a good reason for doing it. Okay, and the return I was hidden before in that animation, but one of the things it did was it turned the I bit back on. Okay. There's even more hidden gotchas. So this is the first gotcha. You can't have interrupts inside of interrupts unless you specifically turn them on. Let's look at some code here. Does the following program work? All right, let's look at the interrupt service routine. It's input, increment, output. Okay, so it's just a counter, right? It counts forever. That's what happens. So what are we doing? Every time the timer 0 has a compare match. So probably in CTC mode, I expect to see a 9. 9, okay. So we're setting up CTC mode in the timer. This is, by the way, how I analyze programs. I kind of jump around looking for interesting bits. So I see timer 0, compare match ISR. Okay, that matches up there. I look for CTC mode. In the output compare value, I put 160. So every 161 cycles, something's going to happen. Every 161 cycles, we're going to output this. And what else do we have? Well, in the meantime, we start 0. We output 0 port C. Okay, so we're outputting 2 different values. We're incrementing port C. So port C starts at 0. And it's going to be going fairly quickly, right? Every 4 cycles, it's doing this. Incrementing. And then this is going to be incrementing port D at a much slower pace. So the question is, does this work? Well, why would I ask the question if it didn't work, or if it did work, right? There's a problem with this. The more astute of you might notice the problem. Anybody want to take a stab in the dark at why this program doesn't work? I mean, it's perfectly legitimate. This loop is going to work just, well, it's not really a loop, right? But this is going to execute every 161 cycles, and it's going to increment port D. This one, every 4 or 5 cycles, going to increment port C.
Does it always return to the beginning of the main?
No. So okay, so that's a question. Does this always return like back here somewhere? No, it's going to be in this loop. And just like the previous example, it'll finish this statement off, go up to the compare match interrupt vector, and then jump down here, and then it'll return to the next instruction. Yeah, Clayton. Galls, right?
Never mind. No, Travis, by the way.
Travis Morzini. I'm there. You're Clayton. You were right behind each other. Okay.
I was going to say something, but that doesn't make sense.
Yeah.
You keep using R20.
Yeah, I do. So let's step through this for a second, all right? So R20, we load it up with 0. And we output it, we increment it, so now it's 1. We're going to do this maybe 4 or 5 times before this interrupt fires. So now R20 is 5. Okay. Now we load up from pin D. Pin D is 0, let's assume. So R20 is now 0, we increment it, it's 1, and we output it. Then we return right here. So it was 1, now we increment it. But it used to be 6, or it used to be 5, whatever it was. So this is what we call a resource conflict. Okay? We've got 2 different tasks. Yeah?
When it's 5, and you go back to that, it's not 5. So it just...
No, it's not 5, because it's just an 8-bit register. It has no smarts associated with it. You're going to say use another register.
No, I was going to say you use push and pop.
Well, if you let me...
Well, we are.
I got like 5 slots. You just... I mean, I know that you don't want to be here, but like, let me like just... All right, so that's the problem, right? These 3 lines use the same register. And yeah, you can absolutely say, all right, well, we'll just use R21 here. That's fine. But eventually, you're going to get to the point where that doesn't work anymore. You can't just use another register. So that's solution 1. Solution 2 is what we call context saving. We save the context. So anything that appears on the left side of an assignment over here, every day at 10 o'clock, that golf cart flies down that hill. We're going to save the register. So before we do anything, we know that we're going to be overwriting R20, so we push it onto the stack. Then we can erase R20, do whatever we want with it, and at the end, we restore its value. Okay, that's yeah, Jimmy.
You said eventually R21 wouldn't work.
Well, it's not that R21 wouldn't work, but using an extra register. Eventually, you'll find yourself using all the registers. And so you can't just pick another register because they all have something in them. Okay. This is more a problem for compiler writers, people who write compilers, than people who write in assembly. But when you're writing in mixed mode assembly in C, so you have a little bit of assembly, a little bit of C, you don't know what the C program's using. So you just have to assume that everything's being used. Okay, so you have to save things. Now, I think this sort of context saving makes a lot of sense. It's pretty easy to understand. Is that a fair statement? There's one that is a little bit harder to understand. Same context saving. We're going to push R20. Now we're going to overwrite R20 with the status register and shove the status register onto the stack. At the end, we pop that, put it back in the status register, and then restore R20. The reason for this, okay, this loop here is a unconditional jump. It always jumps, right? If we're doing conditional jumps, they rely on the state of flags in the status register, right? Well, let's say, and Murphy's Law dictates that this will happen to you. You've got, instead of a jump here, some kind of branch if not equal to, for example. So this increment, okay, let's say it increments from FF to 0. That would cause this branch if not equal to not jump. It would fall through. That's the way it should work. Everything will be fine. But now, here you go from FF to 0. So that's when the interrupt fires, right before the branch not equal. So it jumps in here, and it changes your flags. Okay? this increment is going to change the flag. Even if it wasn't doing R20, it was doing R21, R5, doesn't matter. It changes the flags. So now when you come back out and you go to this branch, it doesn't do what it's supposed to do because you have screwed up the flags. So anytime you're doing things, it's also usually a good idea to save the status register. Okay, and you do it like that. First, you save R20. Then you overwrite R20 with the status register and save that. Then you restore the status register using pop and out. And finally, you restore R20 for assembly. Now, in C, it's a lot easier. Okay, I sort of glossed over how do you know what the address of the interrupt vector is? And the answer is you can look it up in the data sheet. You can look it up inside m328p-def.inc. In C, though, here's a very similar C program. Okay, same kind of stuff. This one actually does do it correctly. Okay, it does reload the T count, which is different from the assembly version we had before. So here, yeah, we set up our I/O, we set up our T count, we set up normal mode, we enable our overflow interrupt enable. And here we just sit there doing nothing. Now we've got some special sauce that turns this into an interrupt service routine. Okay, 4 things that you need every time you use interrupts in C. Okay, the first is you must enable global interrupts. Now we don't have an SEI instruction, an assembly instruction, but we do have a function that simulates SEI. We also have one called CLI, which clears the I flag. So it's a function-like syntax, just SEI, open parenthesis, close parenthesis. So you must globally enable interrupts. You must have a service routine. And the way you do a service routine is there's a very special name. Okay? This one is called timer0_OVF_vect. Everything is vect for vector. And the special sauce in front of it, instead of a return type like int or void, you just say ISR. And that tells the compiler this is going to be a service handler, so we need to use a return I in the assembly, and it needs to go into this particular vector in the vector table. Okay, the names, there's quite a few of them. They are also, you can also look them up, Alex.
Is there any specific reason why main is
To make the compiler quit bitching at me. So main never returns a value, but depending on what compiler you're using, sometimes it likes void, sometimes it's like main, it likes int or void. The compiler we're using likes int, even though we never return from main. It's, in the grand scheme of things, not that big a deal. I just got out of the slideshow. Let's go back. Okay. So we must have a name. There are names for each of these, and it's pretty obvious what the names are. Compare is the compare vector. OVF is the overflow vector, and so forth. That's 2 things. That's 2 things. Third thing, none of this magic sauce will work unless you include avr/interrupt.h. That's what contains all the secret sauce and allows you to use the ISR macro. Okay, the last thing, I must have not put a circle around it, is you have to enable the peripheral. You have to enable an IE bit in one of the peripherals. Otherwise, what's the point? So this name must match the interrupt you enable in the peripheral. Okay, so this is the same assembly version we used before, except now it's using CTC mode. So that's it. Okay. Overall, pretty simple. Okay. So that's timers. We do have one example. Not going to spend a lot of time on it. This is external interrupts. We still have to talk about pin change interrupts, so I'm going to deal with that next. Okay. That's interrupts in a pretty quick way. So I've got about 45 minutes now that I want to talk about the lab. To do the lab, you got to understand interrupts. I know we just did it, and I know the labs today, we're running behind. So what I want to do is go over the phases that are accompanied with this project. So let me load up the lab here. labs. I don't have lab 4. What did I do with it? All right, if I can't connect to the network, I'm just going to go from memory here because I cannot connect up to it here. Just connect long enough for me to get to the M drive. Come on, you can do it. Really? No network access. That's why. So I think when I got it, I put it directly into the M drive, not into my personal folder. All right, that's okay. We're gonna go into open board, and we'll do it this way. So the goal is to basically recreate Lab 3 in C and using interrupts. And it's recommended that you do it in a couple of phases. Okay. Let me just make sure this is all going to get captured. Okay, looking pretty good. So phase 1 is basically get one interrupt working. Specifically, we want to deal with the timer 0 interrupt. Now, phase 1 in the lab, I actually split it up into 2 when I was implementing it for you guys. First thing is just make timer 0 fire at the right time. All right, so things that we know, every 4 milliseconds we want it to fire. Okay, chances are we want CTC mode because that's the one that allows us to do multiple things over and over and over again. Okay, so the first question is CTC mode. Where does the magic number go? Okay, so we're going to calculate some number of ticks, and it has to go somewhere. CTC mode says where that goes. What register does the magic number we want to count to go to? In normal mode, we put like -30 into the free running counter register. What's the other register that we deal with? Remember this figure here? Okay, we compare the free running counter at all times to the value of the OCR register, and that sets off the flag. That's what we're doing here. So it's going to go into the answer OCR 0A. The next question is, what is the magic number? How do we figure that out? Well, with math. All right, here we go, math. Break out your calculator. Make sure it's in engineering mode. We know, so facts. Facts. Our frequency, our system clock frequency, is 16 megahertz, which, by the by, means that our clock period is 62.5 nanoseconds. How did I get, 62.5 nanoseconds. How did I come by that number? 1 over 16 million. We know that we want 240th of a second, which if I do that math, that means that we want our update period 1 over 240 seconds, which is 4.16, 6 repeating milliseconds. So how many ticks is that? Well, I can take this 4.166, divide it by 62.5, -9 nanoseconds. That means that my total number of ticks, is that too low? Do I need to move so people can see? I think I can move this whole thing. Total number of ticks is roughly 66.67 thousand, excuse me, let's try that again. 1,000 ticks, 66,000 ticks. So what do I put in my 8-bit register? What's the largest value an 8-bit register can have? 255. 255 versus 66,000. They're close, right? They're in the same ballpark. So what do we have? What do we have as an option? This isn't going to work. We need 66,000 timer ticks at 16 megahertz. Yeah. Embedded loops is the painful way to go about it. It'll work, right? You can basically set it up so that you take 66,000, you divide it by 255, and that means you are going to overflow 260 times. So it's 261 times. 1 over 240, right? We want to do a 60 hertz refresh rate, 4 digits, so that's 240, 1/240th of a second. Which means you can't even use an 8-bit register to keep track of the loop. You got to use a 16-bit register. Okay. Okay. Those 3 bits in the timer control register tell us what our clock source is. Normally we put a 1 in there, and that gives us an unprescaled clock. But there are other options. Now, in order to do any kind of programming from here on in, it is a requirement, not a polite suggestion, a requirement that you have the data sheet available to you. This is the tough part. I'm going to have to be looking behind me to get to the data sheet. The data sheet has a wonderful table of contents. If you want to deal with the timer, you simply go to that section or that chapter. And generally, if you kind of know what's going on, you have a familiarity with it, you jump right to the register descriptions. Each one of these, and so then you can even look at each register. Some of them are totally boring. T count, OCRA, it's just, that's a number that you put in there. The control registers is where really interesting stuff happens. So if I go over to these control registers, it says, okay, CS020, okay. I then can look at this stuff. 3 clock select bits, select the clock source to be used in the timer counter. Boom, table. Tables are awesome. So we have some options here of what values we can prescale with. So we aren't limited to just divided by 1, no prescaling. We can divide by 8, by 64, by 256, by 1024. How does that affect our calculations? Well, it would be better if I could get to the screen here. So that does affect our calculations. So let's go to another page here. A prescaler, and again, we have 1, 8, 64, 256, and 1024, affects our incoming frequency. So if we start with 16 megahertz in, that means that we could end up with, well, a divide by 1 is still 16 megahertz. A divide by 8 would give me how many megahertz? 2 megahertz. Okay, from there it gets a little bit more interesting. So 16 megahertz divided by 64 is not that because I can't type. E6 divided by 64. Yeah, gives me 250 kilohertz. And if I divide it by 256, 16 E6, I think my second button is a little broken. E6 divided by 256. That gives me, excuse me, undo. Gives me 62 16.5 kilohertz. And finally, divided by 1024 gives me 15.625 kilohertz. Now, how does that help me? Well, it helps me because now I can figure out the new periods. Okay, so this is usually when I jump to like an Excel spreadsheet, because Excel does this kind of stuff really easily. So if I do that, we know that 16 megahertz is 62.5 nanoseconds. 2 megahertz, 1 divided by 2, e to the 6, E6. Yep. 500 nanoseconds divided by 250 kilohertz gives me 4 microseconds. 1 divided by 62.5 kilohertz. Yeah, 16 microseconds. And some of this stuff, like, you should be able to do without a calculator. I just don't want to make a mistake while I'm explaining this to you. And then finally, 15.625 kilohertz. Syntax error. Kilohertz. Let's try that again. Kilohertz. Yeah. 64 microseconds. You can come at this a couple of different ways. You can find out that, all right, 16 megahertz is 62.5 nanoseconds. Then you multiply it by 8 or you multiply it by 64. You always end up with the same thing. Now, what does that mean for us? Well, if we want to go 4.166 repeating milliseconds, we can calculate the number of prescale ticks. So as we said, 62.5 nanoseconds, that's like 66.6 thousand ticks. Okay. 1 divided by 240 divided by 500 nano, -9. Now I'm down to 8.3 thousand ticks. Still much bigger, right, than our 255. I could go to 4 micro if I could use this calculator. 4 micro. Okay, I'm down to 1041. The reason I stopped doing K there, I might be able to have done this with timer 1, right? Timer 1 can go anywhere up to 16 bits. So actually, it wouldn't have been able to do the 66, but it could have done these. Let's continue on. Second insert, 16. Second insert didn't work. 16 microseconds gives me 260 point blah, blah, blah. Still too big. All right, still too big. I need 255 or less. So finally, what do I end up with here? 64 microseconds gives me 65.104. Now, I can't put 65.104 into a timer, okay? So I've got to truncate just the 65. That's the magic number. 65 will give me an interrupt every 4-ish milliseconds. I could go back and do the same thing in reverse and come up with the exact frequency. It's not going to be exactly 240 hertz because I'm truncating the fractional part of the value. Normally, this would be a quick Excel, like grab and pull formulas over. Okay, so we've got this magical number. Now, at this point, if you don't know what to do, go back to the data sheet. Okay? You're setting up this peripheral, which means you got to look at all of the timer control registers or whatever peripheral you're doing. So the one thing I know is I'm going to put 65 in OCR0A. And I'm actually not going to put 65. I'm going to put 65 minus 1 because I want every 65 ticks. So when it goes from 64 back to 0, that's 1 extra tick. That's going to be the 65th tick. So you normally, I will always say 65 minus 1. In fact, you can even see it if you go to the YouTube video. Okay, I put 65 minus 1 so that I know that 65 is the value I care about, and then to make the peripheral happy, I have to subtract 1. So, so then I look at my control registers, and I look at each of these things. Okay, this is the first one. I see COM bits, which we're not using. We haven't talked about them yet. So I'm going to leave them in their default setting, which, by the way, you always know what their initial value is because of, well, the initial value row there. It's all zeros. WGM, though, that's a part of the register we have talked about, the waveform generation bit. So I'm going to scroll down until I see the waveform generation table. And it's not coming up. It's not seeing it, not seeing it. Okay. Eventually, I do get to it. And I know that I want CTC mode. So in my comments, I'm going to write something like CTC mode. WGM equals 0, 1, 0. And of course, you can't see that because I have this up. No, just go away. And then, can I? Okay. So CTs, I'm going to write that in my comments. And now I know, by the way, that some of the bits are in a separate register from some of the other bits, but I can deal with that, right? I can set that up. So the other thing I need to deal with is my clock divider equals divide by 1020, 1024. I needed to do that. So how do I do that? Well, that is going to be, I go back to the data sheet and I look at the CS bits. Where's my mouse? I go back to the CS bits. So here's timer control register 0B, my CS bits. So I go to there. Okay. So if I want a 1024, that's a 101. Great. How do I? Wish it was just a little bit easier to get back to that. So I know that my CS bits must equal 1, 0, 1. From there, I can do this in 2 lines. I can say TCCR0A equals some stuff shifted by some other stuff, ORed with some stuff shifted left by some other stuff. I'll let you figure that out, okay? And then the second line is I also need to say TCCR0B equals, some stuff. The last piece of this, remember there were 4 steps in C to deal with interrupts. What were the 4 steps? Set what? So yeah, global interrupts is going to be a thing. So after all of this setup, we are going to say SEI. That's a thing. That's actually the last thing. What are the other things that I need to do? I'll tell you right now, without one of the steps, this is going to give you a compiler error. It says it doesn't exist. Why? Clearing it won't work either because it doesn't know what SEI and CLI are. Yeah, because we have to do somewhere up at the top include that's not a W, AVR/interrupt.h. I'm pretty sure I spelled that correctly, but there is autocomplete on Atmel, which is why I never learned how to spell it. Okay, so that's 2 of the things down. Third thing, we got to have a service routine. So somewhere else in the program, I'm going to have something that says ISR, and now I need the name of it. The name, you can get a pretty fair guess as to what it is. We know we're dealing with timer 0, so I'm going to write timer 0 underscore. What kind of mode are we in? We're in CTC mode. So I'm going to look at the compare, specifically we're doing compare A, and it always ends with vector. Okay, again, autocomplete will actually help you with this. You start typing timer 0 underscore, it's going to give you a list of options and you can kind of scroll through and then you're good. So what are we going to have here? Well, this is, for now, let's just say pin, what did I use? Pin C equals underscore BV pin C2. For this first phase, all I want to do is just toggle something. I just want to toggle it so that I can look at it on my scope or my logic analyzer and confirm that I've got 4 milliseconds, 4.166. Okay, that's it. That's my whole ISR. This is phase 1. Just make the interrupt fire. Okay, fourth thing. That's 3 things. I've got my include. I've got globally enabled interrupts. I've got my handler. This interrupt right now will still not fire. Yes? Well, okay, RETI is a assembly language instruction. C takes care of it for us. This ISR magic automatically says don't use a regular return, use a return I. Why won't it fire? This interrupt will never fire. Even though we've globally enabled interrupts, don't think global, think. No, in this case we're using CTC, so it's always going. The fourth thing is we have to enable it inside the peripheral. Okay, there is a mask register. Let's go back to the data sheet. This is why it's always good to just have the data. Oh, there it is. Have the data sheet available to you. Where's my mouse? And you look through the other registers. Okay, just look at all of them. Give them a glance and once over. Down towards the bottom here, we see the timer counter interrupt mask register. We need to enable that bit. So somewhere we're going to say TI, you can't see it, can you? Still can't see it. There we go. TI mask equals, or maybe or equals if we don't want to affect anything, underscore BV something. I will let you figure out the something. Okay, but that's definitely something you need to do. This is the fourth step. You must enable it locally. Okay, that's phase 1. Yeah, phase 1. I like that. Okay, phase 1.5 is sort of the second half of phase 1. It's not in the lab, but when I approached it, I said, hey, let's try it out like this. Phase 1.5, redo lab 3 using interrupts. So we still want to generate the same stuff, okay? We have our 4 values that come out. A, B, C, I mean, these could be anything, D, and then return to A. And we have high, low, high, high, high. We still want this kind of output. But now, at these points here, we want an interrupt to take care of that. So instead of sitting here in a busy wait loop, waiting for something to happen, we want an interrupt to fire. We still want a lookup table. So we can actually use those same values, okay? I'll give you, so I'm just going to call this lookup table. Lookup table sub 16. Leave me a little bit of space right here. I'm going to come back to that in a second. And in C, we can globally declare this. OX3F, OX06. So that's 0, that's 1, whatever, to the end, close squiggly bracket, semicolon. We can define that. These are going to be uint 8s, because we are doing it in C. So we've got a type, variable name, size of array, boom. Takes care of all of that load from Z nonsense, except there's a problem. This isn't in program memory. Not at all, not in program memory. So if we want to do a program memory thing, we're going to have a few other pieces. But before we get there, let's write a little function. uint8 underscore t convert uint8 underscore t nibble. This, by the way, is not how I did it. I didn't use a function, but we're going to use this to illustrate what's going on. So you give it a nibble, and it, returns the lookup table value. Well, that's just pretty dead simple. We can just say return lookup table sub nib. If we're being really safe, we might say nib ox f, just to make sure that we don't go over our array bounds. Okay. This is basic lookup table stuff. There's dead simple. We, however, want this to live in program memory. Okay. And dealing with program memory involves the LPM instruction. And LPM doesn't normally come up in C. So we've got some special stuff to deal with it. So to change this into something that uses program memory, we start with a library. Include avr/pgm program space, the word space, not the actual character, space, okay, .h. Include avr/program space. This gives us access to a ton of function-like macros and other things that allow us to get stuff into program memory and get stuff out of program memory. First thing I'm going to do, remember that space I left? I'm going to decorate this declaration with something called progmem. Progmem is just the define somewhere, but it has special meaning to the compiler. It lets the compiler know that this is going to go in program memory. Okay. In recent versions of Atmel Studio, this used to be all you had to do, put program memory there. In recent versions, it also wants you to declare this as a constant value. So that's const uint8 underscore t lookup table sub 16 program mem equals. Progmem turns a little purple when you get into it. Okay. Now, that puts it in program memory. Unfortunately, that now complicates how we get it out of program memory. So, if this is what you did when you were doing it without program memory, everybody agrees that's how you do a lookup. To change it, you're going to do the following. All right, we're just going to add a little bit around this. First, I want you to take the address of that whole thing. Lookup table, nib, and oxf. So you put the ampersand in front of it, address of. Then you enclose that in a call to a very special function called pgm underscore read underscore byte. Now, this is in a family of instructions. Not only do we have pgm read byte, we have read word, read long, read float. We might even have read double, okay? Read byte just gets an 8-bit return value, okay? So that's all you have to do. Yes?
So is that address of lookup table, square brackets, nib, address of...
Nope, it's address of this thing, lookup table sub nib and f. So what this does, lookup table sub nib calculates the address. Address of, so normally that would return the value at that address. Address of says, just give me the address of that value, and then we send that to a read function. All this is really doing is it's doing the same thing. You know, LDI, ZH, ZL, add, ZL, ADC, ZH, R0, LPM. Doing the same thing.
Oh, you're doing the masking in the square brackets.
So the map, yeah, this just makes sure that whatever I put, because this is a uint 8,
Okay.
the uint 8 might be 255, but that obviously is going to do a buffer overflow or buffer out of bounds. Okay, so just to keep that safe, yeah.
Wait, so this statement that we're doing right now, is that replacing the return statement that we have above?
Yeah, well, it's not replacing the return. The return goes there. Okay.
We don't need that other part.
Right. This is a compare and contrast. Okay. This is how you would do it if it was just in data space. This is how you do it when it's in, excuse me, in program space. Okay. You can do a second lookup table for the A nodes as well. Same concept. Okay. It's just the addition of that thing. You can look at this, and I encourage you to look at the header files. Look at them because they contain interesting stuff you might want to use at a later date. Okay. Things like read word or read float. These are things that you might want. Okay. So that's the first thing is we just need to declare some stuff in program memory. Now, the next thing that we're doing is now we're updating our values on our 7-segment display. We've already created a timer that is going to trigger every 240th of a second, give or take, a little bit of precision. So the only thing we're going to do is change what's in our ISR. Timer 0 underscore comp a underscore vector. Okay. So now instead of just twiddling a pin that we can look at, now we've got to deal with some stuff. So I might have somewhere underscore t digit count. So it starts off at 0. And that basically is going to tell me which digit I'm turning on. So I might say, let's put some comments in here first. Turn off all digits. Get new A nodes. Get the new A node values. Put new A node values on port D. Now this might be breaking it up too much. I might be able to get the new A nodes and put it on port B at the same or port D at the same time. But then put new cathode. And the reason I'm not going into this too much, the thing I want to demonstrate here is at some point, right? So this is 0, 1, 2, 3 back to 0. That's what it's going to do to tell you which digit you're enabling. So someplace in here, I'm going to say digit count equals digit count plus 1. Okay, that's it. I could have said digit equals digit plus 1, and then if digit is greater than 3, digit equals 0. That's lazy. This is the fast way to do it. Okay, in an assembly or rather embedded programming, we care about fast. This does with a single logical and truncates that to always be 3 or 0 to 3. There is a bit of a problem though. And I don't know if it specifically rears its head in this instance, but as a rule, this is a problem. If you ran this right now, assuming that all this stuff in red worked, it would never change the digit. Even though you clearly say digit equals digit plus 1, it would never change. And this is sort of because of the way the C compiler looks at interrupts. We never call this interrupt. There is no call instruction. We never do it. If we go back to the assembly, you saw that there was no call instruction. And yet, this code still gets executed periodically. The compiler isn't smart enough to understand that. So what it sees here is, oh, I assign this here but I never actually call this code. So I'll just assume that it never changes in between. Okay? And as a result, what you get is cached values. It caches the value and doesn't actually look it up every time. So there is one more magic keyword that we need to add in here. The volatile keyword. If you have something on the left side of an equal sign inside of an ISR, declare it volatile. Okay? Otherwise, you'll just get the weirdest errors because you'll step through a line of code in C, and unless you go and look at the disassembly, you won't notice that it isn't looking at the memory location. It's just whatever the last value in the register was. And the ISR might have fired since then. Okay, so volatile applies to things that are changed out of normal code flow. This doesn't apply to branches or jumps or calls. It only applies to interrupts because nothing calls the interrupt. Yes?
Is the declaration inside of your main?
So, good question. That's something I didn't specifically point out. This is actually declared globally. If you've ever taken a computer science class, they say that that is the root of all evils, global variables. Don't ever do that. That's terrible. It's awful. In embedded, it's kind of how we roll, okay? Because of scope. What's scope? If you say the mouthwash.
No.
What?
The realm within a variable is like that.
Yeah, the realm in which it exists, the scope. So if I declared it inside of main, as you just suggested, it would only exist inside of main. It wouldn't exist anywhere else. So obviously I can't reference it in an ISR. Now, if I declare it only inside of an ISR, what the hell is the point? I can't use it in the main. There needs to be some sharing of information. So we declare it globally. So it's not inside any function. Okay? Okay, so I've got... Yeah. Okay. So that part is getting everything up and running. Basically, you've redone Lab 3 now with C and interrupts. I am out of time. Okay. I'm just going to go over the steps that I went through for Phase 2. Okay.
I thought we were still on 1.5.
Right, that's Phase 1.5.
Right.
That's it. So Phase 2, the only thing I did... what was the only thing I did? What did I change? Oh, okay. So the last thing, can you guys hang with me for like 5 minutes while I go over this? This is stuff. I missed it earlier in the lecture. Pin change. Yeah, it's Phase 2. Pin change interrupts. Pin change interrupts are a little different from the interrupts we talked about at the beginning of class. This is stuff that is part of your reading. I'm going to go show you where it is on the data sheet. Okay. When we go to interrupts, it talks about all the interrupts that we can have. Okay. And then, external interrupts. I'm sorry. External interrupts talks about pin change interrupts. This is the input section that we normally see in our I/O and what is going on. So this does talk about the same register, those regular int 0 and int 1. But we also have, as I scroll through here a little bit, pin change interrupts. These are 3 additional interrupts. Pin change, interrupt enable 2, interrupt enable 1, interrupt enable 0. Quickly here. Here's our 328P chip. And we kind of have port B, port D, and port C. C, D, B. Okay. Each of these is grouped together into a group of 8 pins. Okay. And there's one interrupt for each of these, which goes to this here. Each one of those groups of 8 corresponds to one interrupt. And we can enable those just like we can with overflow or compare A or compare B. But from that, we actually have an additional layer of masking. So if we want an interrupt on B7. On B7, which is where the button is on the explain mini. We need to first figure out which grouping, 0, 1, or 2. Then we need to figure out which particular pin it is. And it's dead simple. We go to the pin configurations part. And if I can zoom here. Where is B7? It's right here. B7 is PC int 7. That's not pin change 7 because it belongs to one of the groupings. Okay, that grouping, if I go down here, I've got 3 mask registers, PC mask 0, PC mask 1, and PC mask 2. So all I have to do is go and find PC int 7 in one of these 3, because it goes from 0, right here, to 23, okay? Notice it's missing one there. That's because this is C. That's where C doesn't have that extra pin. So what I want to do, I'll go back here now, for B7, first off, I want to enable that, PCIe 0. Then I want to enable PC int 7. Okay, so that's just 2 bits that I need to write in 2 separate registers. Okay, the registers that I need to use, PC mask 0. Okay, so PC mask 0 is the name of the register where you're going to enable the PC int 7 bit. Also, where's my mask? In the PCICR, that's where we enable PCIe 0. PCICR. Okay. At that point, then we will have enabled that pin to trigger an interrupt. The only thing about this, though, is unlike int 0 and int 1, it triggers on rising and falling edge. This is spelt out in the lab part. You have to basically say, if it's high, that's a rising edge inside the interrupt. So it'll trigger twice for every button press. Okay, it'll trigger once when you press it and once when you release it. All right, so you have to make sure that you don't trigger it twice. And that's why phase 2 is just take that value, whatever uint 16 underscore t, right? I just made it OX 1, 2, 3, 4. So that's how I knew if it was working, 1, 2, 3, 4. When you do phase 2, inside of your button press interrupt, which is another ISR, just say num to display plus plus. What does that mean, by the way? If I say num to display equals num to display plus 1, is this the correct declaration for that variable? Because this is going to happen in an ISR. So if that's the case, this is on the left-hand side of an equality statement, or an assignment statement. So this must be declared volatile. Okay. All right. Thank you for sticking with me. I will maybe see you in lab. I'm quite under the weather, so I may be letting Josh handle it today. Okay. I'll try to get this up immediately after class.